Hello and welcome to another edition of Speak Up Portland. I'm your host, Rocco Giannetta, and today we will be traveling 100 feet below the surface of the Willamette River to showcase one of Portland's largest engineering endeavors, the East Side Big Pipe Project. And behind me is a map that will illustrate the depth and scope of the project known as the Willamette River Combined Sewer Overflow Project, begun in 1991. Portland's early sewers were built in the late 19th century, and the city had no sewage system until 1952. By the 70s, due to the city's expansion, the CSO volume had increased to 90 billion gallons per year. Starting at the Ross Island Lagoon, bottom left, we move northward to view an extensive labyrinth of Portland's CSO system designed to remedy that situation. The solid yellow line indicates the completed West Side project. The dotted red line is the East Side project, due for completion in 2010. Before gaining admittance to the project, we needed to be outfitted with a hard hat, gloves, and protective glasses. In addition, we received a safety orientation by Pat Darby per Oregon OSHA regulation. Is this a fashion statement or what? Paul, how you doing?
Good.
Appreciate the time and the effort put into this to bring it to the general public.
Sure.
Could you give us a little bit of our surroundings at this very minute?
Sure. Where we're standing right now is called the Opera Shaft. We're right across the street from the Portland Opera Building, just a little bit off the Willamette River, south of OMSI. This is our main mining shaft. We have a machine, that tunnel boring machine that started here and is headed north right now, is about 1,500 feet away from the Port Center shaft on Swan Island. When that's done, it'll come back here. We're going to put it back down this shaft again. It'll start mining south until we get to southeast 17th and McLaughlin, hopefully by the end of 2010, where the tunnel will be done.
Great.
The funds come from the Portland ratepayers. We exhausted every possibility for outside funding and we're never able to get any. But the Bureau sells capital bonds every 2 years, and those bonds are paid off by the Portland ratepayers. But those bonds are what fund our capital program every year.
Paul, actually, what was the impetus for this whole project, and when did it start?
The CSO program, the Combined Sewer Overflow program, basically started in 1991, where the Bureau signed what was called a stipulation and final order with the Oregon Department of Environmental Quality to clean up combined sewer overflows from the Willamette River and Columbia Slough. It was the start of a 20-year program, so this is 2009 now. We're 2 years away from the end of the program. These big tunnel jobs are kind of what we push to the end because they're the most expensive and you don't want to spend any more money than you have to, but we should be done with this in 2 years, and that will signal the end of our 20-year program.
That's amazing. We're on schedule and on budget.
We are slightly under budget and we are on schedule right now, yes.
Fantastic.
Well, the tunnel itself is made up of concrete segments. And what you see here is 2 stacks of 4 segments each. This represents one ring of the tunnel. So basically these are lowered down and taken to the front, and the machine will put these all in a circle. We've got these 8 segments that make a ring. Now there's a reason to pay attention during your high school geometry class, because this consists of 2 trapezoids and 6 parallelograms. So bottom segment is the first trapezoid that goes into place. And then parallelograms are built around each side of it, and the last piece is what's called the key, which is the smallest trapezoid. And that key is then inserted in there, and that's what puts the pressure on the rest of the ring. And then the machine pushes itself off the last ring. Here you can see the gaskets. These gaskets then match up, and the pressure of the ground and the water push this ring together and keep the water from going in. And these gaskets press up against each other and keep all the water out. That's why you can see when we're down there, it's a very dry tunnel, even though we're 100 feet below the top of the river. In effect, when the machine goes through the ground and the segments are installed inside, it leaves what we call the annular space. As the machine moves forward, the steel shield moves forward, they fill that space with grout, which is what that little plant is for. That's where they mix the grout. That's then pumped around the segments to fill that little void, and the reason for that is that we didn't want that to collapse in so that it goes up to the surface and causes any kind of settlement. So that little space outside the segments is filled in with that grout, and then that that pressure from the ground and the water is what, basically keeps these segments together.
And also the grout can fill in any little gaps?
Yes.
There you go.
Any little gaps.
That's why there's not that much seepage.
Right. Well, before we start the job, we actually go through what's called a risk analysis, and we go through and we think of everything in our experience, the contractor's experience, designer's experience, that could possibly go wrong. And we put that on this big long list, and then we assign a probability to it, and we assign a cost impact to it. And the first thing we try to do is for every one of those risks to see if there's a way we can either design it out or do something that gets rid of that risk. The rest of them, we kind of assign a cost to it, and we carry that as a contingency off to the side. It's not part of the contract with the contractor, but as a bureau, we carry that budget off to the side in case we need it.
Like an insurance policy.
Like an insurance policy, right. So we have had some things that didn't go the way we had planned that cost a little more time and effort to do that we've covered with that contingency, but at the same time, the machine has gone a lot faster than we had planned. The work has been even more efficient than we thought, and so we've saved money on the other end. So far, we're actually tracking under the amount of money we had anticipated to spend by this time.
What it's called, the floor?
Bottom of the shaft.
Bottom of the shaft?
Yep.
what are we looking at here?
Okay.
And how far up or where are we?
Okay. Right here where we're standing, we're about 35 foot back from the very front of the tunnel boring machine. Where we're standing here is where we're bringing in our segments to build the rings. So as you see here, we're building concrete rings basically as a ground support as we're pushing forward with the TBM. And segments get brought in. There's 8 segments to a full ring, a 5 foot long ring that gets unloaded here. We have these vacuum hoists. So basically there's a vacuum plate that goes down, sits, picks up one segment, moves it front, goes down on the little sleigh here, pushes it up to the erector, and the erector, again with the vacuum plate, goes down, grabs the segment, and then moves it up into position and sets it in place. And then starting in a clockwise position, goes all the way around until we have the 360 degrees until we have the full ring built. And then we have laborers. So there's we have one laborer running the segment erector. We got one laborer running the hoist to bring the segments up to the erector, and then we have one laborer actually installing the bolts in this operation.
In keeping the tunnel straight and online, we use GPS?
No, we're actually using a theodolite system. So we have an automated theodolite system that constantly monitors the position of the tunnel boring machine. So it shoots back to targets installed in the tunnel and then shoots up to the front of the heading. And that's an automated system, so the TBM operator, so the guy controlling the TBM, he constantly have feedback and he knows exactly where the position of the TBM is in relation to where the designed alignment is at. In this case, it's a 500-ton, well, in total here we have close to 1,000 ton with all the backup system. So the full length here of the tunnel boring machine and the backup is about 250 feet. But the front end is the real business end of the operation here is about the front 35 feet, and that's what you're looking at here. Going forward, that's a tunnel boring machine. It's 25 foot, just over 25 foot cut diameter, and our inside diameter of the final liner is 22 foot. There's one operator. He runs the machine itself. So he controls the front forward movement of the machine with all the thrust jacks, as well as the rotation of the cutter head. But also what's probably as important is that he controls the whole slurry system that keeps circulation going, taking out the muck as we're excavating forward. So we have, this is the first pump that we have on our slurry discharge system. It's about 850 horsepower pump that pushes the slurry out through the tunnel up to the separation plant up on surface. And that's how all the material that we're excavating is brought out of the tunnel. About 100 foot below the water table. So we all the time have to control the groundwater that otherwise would come at us. So we keep a constant pressure out in front of us of about 3.2 bar in order to maintain stability and not basically be dewatering the ground in front of us and have an inrush of water.
Do you come across any big boulders, or is it just mainly dirt?
I'd say it's mainly dirt, but over the last 1,000, 2,000 feet, we have encountered a lot of boulders, and up to say 5 foot, 6 foot in diameter is what we've seen when we've been out in the working chamber.
So this machine can do dirt and rock also?
Yes, it has disc cutters that are capable of basically cutting up rocks in 5, 6, 7 foot diameter. The cutter head itself is equipped with disc cutters that will grind up the rock to say maybe less than 2 foot diameter pieces. But then it goes down into a stone crusher just before it makes it into our discharge pipe. So there's a stone crusher that constantly grinds away and crushes any rock that comes down to the discharge point. And then we have grizzly bars basically in front of the discharge pipe that reduces the size of any material going through to about 6 inches in diameter. Yeah. We have a fan set up at one of our shaft locations that's blowing about 30 to 40,000 cubic feet per minute into the tunnel. So it's keeping...
always a nice flow there.
Yeah. We had about 18,500 feet out right now. And we have another 1,500 feet to go before we come up to the end of our north drive, and where we'll be pulling into our port center shaft up at the Swan Island location.
Right.
Yeah, the entire 18,000 feet here that we mined goes back to the opera shaft site and run through our separation plant and get loaded out on barges onto Willamette River. We're working on one of the compensators for the slurry discharge system. So basically this is a compensator, is a rubber section of the steel discharge line to take up any movement as we are pressurizing the system, as we start up or shut down the system. So any bit of movement is taken up in the compensator. So that's what they're exchanging and finishing up the exchange up right now.
It takes a lot of muscle to do this.
Oh yeah.
Also a lot of balance, because these guys are not standing on anything that's flat. It's actually a circular surface.
Mm-hmm. Yes, it's a very crowded area.
Right, right. Right now we're in the TBM office, and with me is Tracy Cordova with the V. Tracy, how you doing? And possibly could you tell us and our audience what we have going here?
Yeah. This is the TBM cabin, tunnel boring machine, for the northbound CSO. We started the stone crusher, and Father Eddie looked at it. He's the one that fired it up. He said it's actually, the numbers are better than they have been. The block is not containing the pressure that it was before, he said. So when you would shut it down, it would keep a little bit of pressure, and he says it no longer is doing that. So he's... Okay. Okay, Klaus? Like I said, I was saying around noon. They're putting it in right now. I would say between 12 and 1 now. So, but it's going in there right now. That compensator is a little tight, but it is going in. And they haven't put any bolts in there as of about 5 minutes ago. I was down there, and they haven't put any bolts in yet. But it's going in tight, but it's going in. I'll call you back here shortly. Okay, bye. We're about a little over 3.5 miles in. Got about 350 rings to go before we pull through. Just an overview of what we have here. The way the machine operates. This is the slurry circuit, is a slurry tunnel boring machine. You have a series of feed pumps and return pumps. Your slurry circuit, your feed side, this brings in your fresh bentonite from the separation plant, which is located up on the surface, right at the OMSI area. You start your slurry circuit up, you get your bentonite, your material moving throughout the pipe. Your feed pumps, you open your valves going into the excavation area. Your cutter wheel is in this area here. These illuminated lights here are the level of the bentonite in the working chamber. So when we are firing up to start mining, I will fire up the feed pumps, return pumps, get my slurry board going, open up desired valves. What floats the material, the bentonite, has a certain value to it, which it's like a thick pudding, and it floats the rock, making it easier to extract as you're cutting it with the cutter head.
Right.
So your return pumps will suck that out of the excavation area and into the tunnel up to the separation plant, where the separation plant will filter out all of the spoils and send back the fresh bentonite back to the tunnel boring machine. Yes, sir. That is the VMT is laser guided. Actually, it is just sitting right out here outside the window, but it is a Leica laser, and it shoots a target at the front of the machine, and you just steer accordingly. It updates every so many seconds, and you just steer the machine according to what it's giving you here.
So what your parameters are.
Yes, sir.
So I'm assuming that this is dead center, and these are the outsides.
Yep. Right now, horizontally, the rear of the machine is sitting at about -9 this is all in millimeters. So
millimeters, it's incredibly tight.
It's basically right on the, I mean, anytime you're within 10 millimeters, I mean, for a machine this size, it's pretty much right on the money.
Pretty amazing, yeah.
Yeah.
And this is just a replication of this over here?
Exactly. This is all the pumps that we have in our feed pumps. This pump right here is at the separation plant. This one is in the tunnel. This one is on the TBM. This return pump here, we've got 6 return pumps. This pump right here is on the tunnel boring machine, and these pumps are throughout the tunnel. By the time we start this machine mining here, this is the belt up at the separation plant. Once we start the mining process here, it takes about 45 to 50 minutes, or about 45 minutes right now for the material. As soon as I open that valve right there and start pulling material, you'll start seeing material right here in about 45 minutes. Yeah, we just monitor these screens as we're mining. What these are the thrust cylinders for the tunnel boring machine. You just stay within the parameters, the speeds that the bosses have set. They would like to see the machine running through whatever geology you're running in right now. We're in some pretty big boulders right now, so we're mining very slow. It takes approximately 2 hours to complete a 5-foot push right now. We're mining ahead, I would say, at about 16 millimeters a minute. So these cylinders right here is just a duplication of right here. This is how you steer the machine. So these potentiometers here, that's how you steer the machine. These here, this is our grout system. Right now we are doing work on the cutter head. The cutter head is, the tooling on it is taking a good beating right now in these big boulders. So that's why we're mining so slow, making sure we're chewing up these rocks and letting the stone crusher do its thing. And, to get comfortable with the machine, it took me, I would say, about a good 2 years to really just to get comfortable with it. It's a high stress job. Very demanding. There's really nobody to sit in for you besides the other operators working a longer shift. But yeah, it's a wonderful job, and it's very rewarding.
8-hour shift?
Yeah, it's about a 9-hour shift right now. Yeah. So by the time we do our shift change, and come from the underground gold mines in northeastern Nevada, so I've got underground experience. No tunnel boring experience as of 2000. And like I said, I was just trained on the west side by Impergilo Healy and some Europeans that were on the tunnel job.
So Tracy, thank you very much.
Thank you.
Interesting work. How do you like the job? I mean, is this
I love it.
Lovely? Yeah. It's a comfortable environment for you, and the camaraderie is good.
Yeah.
Got a bunch of characters down here, I can tell.
Yeah, you never see nothing like it.
Niels, the question was, in the business, your industry, do you guys have a moniker, like a nickname, like the Tunnel Rats?
Let's say here it's mostly miners.
Miners?
It would be sandhogs.
Sandhogs?
Yes, they are miners, working together with Portland's environmental services, engineers and their staff, and the skilled workforce, harnessing the power of machines to ensure Portland's future environmental health.